hell out of here.
Go, 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 go! November 9th, 2018. This was the day that our TA, TJ Blackburn, set off a chemical reaction in the lab that turned everyone in a 50-mile radius into brain-eating zombies. Me, Abel Cherian, and my lab partner Nathan Gill were working right alongside him, but somehow all three of us were protected from the chemical reaction because this mysterious white powder fell on us. This was the cure, but before we could do anything with it, a horde of zombies massacred TJ in front of us. We managed to fend them off long enough to collect a sample and gather some analytical tools to figure out what the substance is. Now, we're in the desert. This is the only safe place so that we can conduct our research and figure out what this thing is. May God help us in this endeavor, or we're all screwed.
Dude, what are we gonna do?
Well, we managed to take some of these machines before we had to evacuate the lab. We have this. It's all that's left for us.
Dang.
We can't even use half of these machines anyway.
Wait, what do you mean we can't use half these machines?
Well, a lot of them don't have any application to figuring out what this thing is exactly.
How
like
so?
Here, we've got the thin layer chromatography machine, which uses a stationary phase and a mobile phase, and uses intermolecular forces as a differentiating characteristic. But we know that our substance is pure.
Right.
So we don't need to know its intermolecular force strength relative to other things in the mixtures when there's only one thing in there.
Right, because we're not splitting anything up. So, yeah, I see what you're saying. What else?
And then beyond that, absorbance spectroscopy, once again, that's only useful when we have a mixture and we want to know concentrations. Because this uses a differentiating characteristic of quantization of electrons, and different electrons absorbing different wavelengths to become excited and actually absorb them. And so this will tell us, if we have a mixture, the concentration of different things in a mixture, but since we only have one thing, it's only going to show us one wavelength that's absorbing.
Okay.
It's not going to be useful.
Yeah. Wow. That's crazy. Wait, what about the GC? Right?
Well, maybe the mass spec part of the GCMS, but the actual gas chromatography isn't useful for a lot of reasons. What the gas chromatography does is it uses intermolecular forces, and kind of like the TLC, there's a mobile phase and a stationary phase. This time, when you inject something into the GCMS, it's going to transition between the mobile phase and the stationary phase, where in this case, mobile phase is actually gas, and stationary phase is the liquid. So if something has a higher boiling point, it's going to stay in that liquid phase and have a longer retention time to go through the entire column in the GCMS.
Right.
So for us, it wouldn't be useful because since we only have one substance and it's pure, you're only going to get one retention time of one thing going through the GCMS.
Right, and there might be like other peaks, but they're not really representative of that pure substance, right?
Yeah.
Yeah. All right, so we don't really need the GC either. Yeah, but wouldn't, like, for example, F-tier work, right? Because Fourier transform infrared spectroscopy uses infrared radiation to excite the bonds in certain molecules to some kind of vibrational transition, whether it be like wagging or wiggling or something, right? And then the machine picks up that vibrational transition or that amount of energy that it's required to excite that bond and reveals that to the person, right? And so basically we can use the amount of energy that the bond is required to go to that vibrational transition as a differentiating characteristic to tell what the bonds present in the molecule is, correct? And so as a result, we can basically tell what bonds are in the molecule. We can tell like what the molecule basically is made up of, right? And another important tool that we have here, like you said, the GC might not work for us, but the MS clearly does, because in mass spectroscopy, the amount we basically ionize the molecule that we're given and we break it up into different fragments. And basically the benefit of this tool and the differentiating characteristic of it is just basically the fragments that's created, right? And so we have these it basically just gives us the molecule, it gives like a ballpark estimation of like what makes the molecule, like how many carbons, how many hydrogens, how many oxygens is in the thing, right? So it just tells us actually like an estimate of what the thing is. But also one of our biggest tools that we somehow got our hands on in the lab was the 60 megahertz NMR, because in nuclear magnetic resonance, right, we can actually tell the hydrogens and how they're organized within that molecule, which is like one of the powerful tools we can use, because it basically tells us what the molecule would look like, right? Because it also fires some kind of energy in which the protons absorb it, and that basically how much energy that's used, or how much energy is absorbed by that proton. In this case, it's hydrogen protons, because this is an H NMR, right? How much energy is absorbed, we can use that as differentiating characteristic to tell where the hydrogens are around the molecule, what other hydrogen regions are around that molecule. So basically, we have all the tools that we need to figure out what this thing is. And you're right, we just have to use the F tier, the MS, and the NMR. So in the mass spec, we need to find the molecular ion, the rightmost peak, and the peak that has an even MZ, because anything that's not even usually means it's an isotope or it's an anion. Well, the rightmost and the even ones, the two answers could be 116 or 138, but 138 is, the peak is way too small, so we believe that the answer is 116, and that is a molecular ion, or the molecular weight of the molecule. As a result, this reduces the possible choices down to a molecular formula of C5H8O3 or C6H12O2 or even C4H4O4. For the IR spectra, the peaks reveal that the bonds that are within the molecule include an OH bond, a CH bond, a C-double-O bond, and a C-double-C bond. But what's not in the molecule is a C triple bond C bond or a C single bond O bond. So we now know what bonds are within the molecule and what the molecule kind of looks like, which will help us to identify the molecule. So in this NMR, we see that there are 4 different signals. Now the 2 peaks that are around 1.5 to 2 ppm, they do not count because we believe them to be the solvent peaks, but the other 4 signals count. So for the first signal, it is a signal at 7.71 ppm, which is an integration, and it has 4 peaks, which means it has an n equals 3. Then the second one is at 6.31 integration, or 6.31 ppm, has an integration of 6.31 ppm, and it has 2 peaks, which is an n equals 1. The third one has an integration of 4.91 ppm, which also has an n equals 1, 2 peaks, n equals 1, which is 2 peaks. And then the last one is at an integration of 0.31 ppm, which means it has 1 peak, so that means that it's an n equals 0. Given the IR spectra data and the mass spectra data telling us that the molecular weight is 116, and the fact that this substance is a white crystalline powder, our best bet for this molecule, for this cure, is levulinic acid, or 4-oxopentanoic acid, which is a white crystalline powder that meets all the above criteria. The only issue with this molecule is the fact that its predicted NMR doesn't match up with our NMR, because the peaks are different integrations and the splitting is all weird for the predicted, is all different compared to our NMR. But we believe that this can be the NMR can be neglected because there might have been some injection issues or some kind of contamination. But we truly believe that the cure is levulinic acid, or C5H8O3.
Got it. We found the cure.
We found the cure. Now we have to go back. We gotta save all those people. Are you ready?
Yes. So, we're going?
Yeah.
Oh.
Let's go.